back to physical chemistry. Today what I would like to think about is how the spectrometers of the different types of spectrometry that we've looked at already can be put together, what the pieces inside them do. So I'll have to draw some stuff over here on the board now. In the simplest possible type of spectrometer, we would have a light source, some kind of lens. Our sample could be here or it could be over here, and we need some way of splitting the light up into different colours. A simple way of doing that would be a prism, although it's not the best way to do so. If we split the light in this way and we have our sample here, we need a lot of detectors over on this side to detect the light. And if we have our sample over here, then we only need one detector. But we need to be able to rotate this prism so that our detector gets the light one colour after another. There are advantages of both types, so if we send the light through all at the same time, the advantage is that we're measuring all colours at once, and so our spectrometer is fast. This will be a visible light spectrometer to start with, which means that our bulb is a simple bulb which is giving out lots of colours. That is, unless we want to measure only one colour, in which case an LED would be better. LEDs are not good for generating a wide spectrum of colours, so even in modern spectrometers we typically use that sort of old style light bulbs. The good thing about visible light is that lenses are comparatively simple. They can be made out of glass or polymers, and the light will then go through and it will be fine. If we want to use ultraviolet light, then we will have to use a special bulb here because we can't get into ultraviolet light with a normal bulb. The other problem of ultraviolet light is that it doesn't go through very many polymers, that our prism would be a problem if we're going through it, and that it is advisable not to use this method where our sample is here, because our sample will be exposed to ultraviolet light the whole time that we're measuring, and so it's better to come up from the long wave ones to the short wave to minimize the amount of damage that we get in the other colors. Obviously we can't stop damage from ultraviolet light if we're going to measure in the ultraviolet region, but we don't have to have it in the rest of the spectrum. The first upgrade that I would like to do to the spectrometer is to convert this prism into a diffraction grating. You may have come across these in physics. So diffraction grating will go on here, and it's very similar. It's going to cause splitting of the light into its component colours. The big difference is that a diffraction grating is a series of lines in a mirror. So the light comes along and it is reflected off the lines effectively, and it can constructively interfere in the direction that we're looking, or destructively interfere, so we get a splitting of the colours by the separation between the lines and the angle effectively. The good thing about a diffraction grating is because we're using reflection, it is not so tendency. It has a very low tendency. That's a bad way to start that. But it has a very low tendency to absorb, so we can use it for different colours. But still, the distance between the lines on it will be somewhat dictated by the colour range that we're using. So an ultraviolet filter or an ultraviolet diffraction grating is not very good for infrared. Still, we will see them in most of our other devices. Likewise, our light source will be limited to exactly what we want to do it, and any lens that we use will obviously have to be transparent to the colour that we want to use. Now we get on to the detector. Obviously we need to detect the light coming out, and that is sometimes a problem. So what is the most common way to detect light at the moment? And that would be the camera chip or child device, CCD, which you are familiar with from the camera that I'm using to film this, or the camera in your phone camera in your computer. They're all the same. They use a charge coupled device to convert light into a digital signal, and we can use a linear one of these to take all of the data if we use a grating. So some of our spectrometers are exactly designed like all of the light comes in, it goes through the sample, and then it goes through goes onto a diffraction grating, is split into its component colors, and goes onto a charge coupled device almost exactly the same as the one in the camera, except it's very long and thin, and that's so that we only have to split the light in one dimension. We only have to have an angle in one direction. Now, spectrometer can be relatively small. The alternative would be to have a more sensitive way to measure the light, but let's first of all look at a CCD. In every pixel of our charge coupled device, we would have an electrode, and when a photon comes along, whoops, let's have it as a wiggly line. When a photon comes along and it's hit our semiconductor underneath the electrode, it generates an electron-hole pair. So we generate an electron and a hole, and if we have a field, so in this case it's a positive field, we would trap the electrons here and we'll repel the holes out to somewhere else, typically to ground. Then we'll generate a little cloud of electrons underneath this positive electrode. If we have another positive electrode nearby, it will be collecting electrons, so we can generate an image. When we want to read it out, we fiddle with the potential of our electrode to get them to go to a measuring device, and we measure the charge, which is effectively the current that we can draw out times the time. So depending on how the chip is, so with a linear chip it's not quite so hard because we don't have to shunt it very far. With a camera chip such as the one in the camera that I'm using here, each of these have to be pushed along, gradually shunted along and measured one after another, which limits the measurement speed. Note that when this is full, when we fill this up with electrons, when we balance the charge effectively on this electrode, we can't actually get more electrons in there. Any extra electrons will float away and they might interfere with the next pixel. So it's important that we don't overexpose our pixel. However, what we see is that it's not a brilliantly effective device. Depending on the color of the light, we may get more or less photons, and so we may have to account for that in software afterwards. Depending on what the material is, if we have the light coming from the top, we might have a problem with loss in our electrode. If we have the light coming from the bottom, which I've drawn here, which is a more obvious way to do it because we're then not going through the electrode, then we've still got to get into our material and it could be absorbed in other ways, so there are going to be holes in our spectrum usually. What we find is commercial ones, so a commercial camera CCD is sensitive to all colors of visible light, but it's also sensitive outside the visible region. It goes reasonably into infrared, but not very far, but it goes quite a long way into ultraviolet. So if we take all the filters off and any lenses that are on our camera, we can detect both infrared and ultraviolet, although it's pretty much only near infrared that we can detect with these. Our infrared needs a different type of detector, and as we can see, yeah, we're going to need a lot of photons for this because it's not super sensitive. Staying in the visible region, let's think about Raman for a moment. So if we want Raman, we need to put in a lot of photons of one color, and we need to measure extremely sensitively. And now we're just not going to get away with the types of measurement that we were doing up till now, although Raman spectrometers like the one that I've got do exist with a CCD detector. They have to be comparatively expensive ones, but they work fine. If we want to get more sensitivity out, then we're going to have to use a better type of detector, a more effective type of detector, and obviously our light source should be a single color, and so we're going to need a high power LED or a laser to do that, because then by definition we're only going to get one color. So let's have a laser, It's an acronym, so oops, laser. We can have a lens there because typically we would use visible light for Raman, and we don't need a grating. On the input, we're going to hit our sample. We don't want any of the laser light to go to our detector because that's not the color we're looking at, so we will look at it at some other angle, typically 90 degrees, but it could be some other angle. We don't want to look at it directly back, and we don't want to look at it directly forwards because we're going to get a lot of light from our laser back. But even in scattering, most of the light that we see will not be the light that we want, so we need some way of blocking it. So instead of having a grating to split our light up, we're going to use a filter. A filter will be a piece of glass, because we're using visible light, with coatings on it to absorb a single color of light, that being the one of the laser. And we do that by having different optical densities, so different refractive indexes, and each stack will be about the same length as the wavelength of the laser in that material, and we will reflect, or then we'll reflect most of the laser light back out and only transmit other colors. This is known as a notch filter, and they're comparatively expensive. That's one of the more expensive components, but we've got a laser, so it's not going to be a cheap device. Then it's going to go to grating, because we still need to be able to measure the wavelength, and then we're going to want to measure the number of photons that we get relatively accurately, because we might not get very many. We are slightly familiar with how that works from our previous episode into XPS and EDX. So remembering what happens in EDX, we have an atom. It has some electrons in it. Whoops, our atom has blue. It's got some electrons in it, and they can be knocked out. Let's knock out an outside electron, because those are the easiest to knock out. We can excite one of those electrons with a photon, which would be a primary electron, and that gets knocked out. That wasn't the effect that we had. We had in our electron microscope, an electron comes along, and it shoots out an electron from our atom, and the one that came along also continues, because the energy is distributed. The energy of the incoming electron is distributed between the two electrons that leave, and because we can't tell which is which very easily, there are ways, but it's not that easy to do, we will struggle, put it that way. We'll struggle to get information from these, but we do have twice as many electrons as we had to start with, which means if we can keep this process reasonably efficient, as long as we don't lose too many of our electrons to other things, we can make double as many electrons, which is good. So that gives us an idea of how we can make a very efficient photon detector. So here is how we would set it up. We have an electrode. We can make this slightly negative to motivate the process to help. A photon comes along, it hits our electrode, and it knocks out an electron. So we've got photo-generated electrons. We can modify the surface to make it better, to make it more likely to give out electrons in the wavelength that we're expecting. But this comes along, and we can cause this electron to come and hit another target if we make this slightly positive compared to the first electrode. That will cause the electron to be steered towards it, and it will knock out some electrons, which will be caused to come to the next one, and then to the next one, and then to the next one, and then to a cup, which will collect all of the electrons from the last electrode and count them. Counting them is done by measuring current and time. Obviously this like the charge coupled device, has a time. If we hit it with another photon before the first one has gone, we're going to get lots and lots of current, and which isn't actually that bad in this case. They're comparatively fast. We will see worse detectors in a moment. We will obviously have to have vacuum in here, otherwise the electrons are going to hit something and that will slow them down and they won't do the thing that we want. And we can couple these up relatively easily so that we only need 2 contacts or 3 contacts to here and resistors in between to generate the field difference between all of the electrodes, and 1 for the end. Then we can measure photons relatively accurately and extremely sensitively. So now we can count single photons if we have enough stages. Obviously, there is a question of color, because we can't necessarily tell what the color is because we're counting electrons at the back here. So if the light gives off 1 electron or 2 electrons at the beginning, we don't know. At the end we just count how many electrons are coming, and if we don't have single events we can't count photons, which is why it's a good idea to have a diffraction grating. I forgot what it was called then. If we have a diffraction grating in between, then we can measure the color of the light at a separate instance, which does mean, however, that we're not measuring all colors of light at the same time unless we have a whole load of these, and they're not super expensive. So it is possible some machines do have an array of photomultiplier tubes in order to measure faster. The problem with Raman is obviously that we've got a laser and it's going through our sample somewhere, and that can cause damage to the sample. So if we are shooting it for a long time with our laser to try to get a lot of spectra, we may cause it to change while we're looking at it, which is not helpful. Much of the design of spectrometer will depend on what it's going to be used for, and so many times, or many of them, are set up in relatively standard ways because of their normal use. So if we take a UV spectrometer, which is going to be used to measure the amount of things, and we're going to be using a logarithmic scale to do so because of our so now that I've remembered what it's called, it's the Beer-Lambert law that tells us the concentration of something in a measurement using the log of the amount of light divided. So it's effectively the ratio of the light compared to the incoming light, and the log of that. The log to the base 10 is typically used, and that is obviously a problem because it means that if we are going up in concentration, we have to go up non-linearly in light. So if we have an absorption of 6, we're getting 1/1000th of the light. We need to measure that accurately. That's going to be challenging, to say the least. So the problem there is that everything is variable. So if we have our simple spectrometer, which we have in our lab, we've got a single light source which is split into 2 beams by a half-silvered mirror. So that's a mirror that's not very good. It lets some light through down the reference path, and it goes to 1 detector, and some of the light is reflected and goes to a proper mirror here and goes through the sample. Then it goes to another detector. The strength of this compared to measuring a reference first and then measuring the sample is that this will take out any waves in the light source and maybe the electricity source. Also, if our detectors age and our samples do something, so our reference sample is going to absorb some light, it will be a empty cuvette, the container that we put our sample in, with the solvent that we'll use in our sample. Typically UV fizz is done in solution, although it isn't always, but we would want our reference sample to be the same as sample as much as possible. So here we have 2 weak points, the weak point being that the detector might not age the same, and this partially reflecting mirror, which may or may not be 100% effective. they're pretty good. This system works very well, and it's very simple, and it has no moving parts, which is very good. If we go to a more advanced type of spectrometer, which I've given back because I couldn't get it to work, a more advanced type of spectrometer only has one detector, and it only has one beam at any one time. So it has a mirror that rotates, and so half of the time the mirror is in there and half of the time nothing's in there. So it rotates in on a different axis. It's on a wheel. It's effectively a fan, but when it is in the path of the beam, it goes down the sample, for example, and when it is, so this goes into the same detector, and when it is out of the path of the beam, it goes into the reference. And so half of the time we're measuring the reference and half of the time we're measuring the sample, which means that if we have very short wave in power supply and it changes the brightness of our lamp, then it may falsify our result, but it would have to be exactly fitting the cutting of this, because otherwise we will eventually get to a different mirror, and so then we will be measuring again effectively the same thing. We obviously have to cut our light somewhere, so we would either do it before or afterwards and split it into colours so that we can measure it. Typically it's done beforehand, which I haven't left space for. So typically we would have a diffraction grating in here. Let's have it in here and reflect it back up. So typically we would have a diffraction grating in here to split up the light and rotate it to get different colours one after another, and each colour will go through the sample and the reference multiple times, and the difference between them will be measured at the detector. Effectively we can electronically get the absorbance immediately without doing any calculation inside a computer. The detector can just have some electronics to do that. That is both quick and extremely accurate. A spectrometer built like that can get up to an absorbance of 9, which means there is 1 billion times as much light in the in the reference beam than there is in the sample beam. That is amazing that you could get up to such a high precision, considering what a normal camera can do. If we had a CCD as this detector, it would have no chance whatsoever, because the range of brightness that a CCD can manage accurately is nowhere near high enough to be able to do that. If we want to measure fluorescence, we have several advantages, which is why fluorescence is quite attractive for measurements in biology. We can use an LED as a light source, which makes it comparatively cheap and long-lived. It has to be relatively blue. Ideally we would have a slightly ultraviolet LED, so that we can get as many possible types of fluorescence. But if we look at a typical absorbance band of a fluorescence, it will have a long tail to ultraviolet. So it means that as long as our light is blue enough, we will see some photons of fluorescence. The good thing about fluorescence is that if we have a diffraction grating and everything is in the dark otherwise, there shouldn't be any light of the wavelength that we're looking at apart from fluorescence. So if we put in blue light and we expect to get out green, then we can set our diffraction grating so that we're looking at the right wavelength or in the right range, and our detector will only see light when fluorescence is available. Likewise, we could have red fluorescence, or blue fluorescence does exist, but obviously we'll have to shift into the ultraviolet to be able to activate that. If we want to measure the absorbance spectrum, then we don't want to measure this part. We first of all have to find the band, and then we would need to change colour here. Obviously a simple fluorescent spectrometer wouldn't be able to change that. If we have a better one, we would have two gratings, one on the output path and one on the input path, so that we can measure both the absorbance spectrum while measuring the fluorescence, and on the emission spectrum. But that's really only for investigating fluorescence. If I want to just measure if something is fluorescing or not, then I can just put in one color of light and it's fine. As you can see, we've got this 90-degree angle again, because then we don't get so much extra light from the LED coming out, and obviously there is a danger that any of the other components might fluoresce and generate light that's going to get in the way. Our detector is sensitive to the light, so any light that's bouncing off the bit of the diffraction grating that shouldn't be reflective will go in the detector as well, and that's not good. So we do have to pay attention to the materials used and maybe have a filter in front of our detector for the color of the LED, but it's not as bad as Raman because you get a lot more photons out. The quantum efficiency, the number of photons that you get out for the number you put in, is not bad for fluorescence, whereas for Raman it's 1 in a billion, maybe 1 in a million if you get lucky. Obviously we would like, because it's ultraviolet, we obviously need to collect that light and not just let it out into our lab, because that would be hazardous. Infrared is different. It's different because we typically look at far infrared. Near infrared is a lot more like visible light. Far infrared, which is what we want to use for measuring molecules, for determining which molecule we've got, the one that is important for this course, is easier in some cases because we're just going to use a hot bit of stick as our light source. I think I mentioned it before, but it's just a piece of silicon which we pass current through. It gets warm, it doesn't have to be really hot, and that's it. The good thing about it is that that lasts a really long time and doesn't cost a super amount of money. The bad thing is it takes a while to warm up, so you have to turn it on plenty before you want to use it. It emits a lot of infrared photons, so that's good. It's a very bright infrared source. The bad thing about infrared is it doesn't go through very many things. So we need to have maybe a window for it to go through so that we can get it from one part of our machine into another. Maybe we'll do without to start with. Let's not bother drawing that. We'll draw one window. We might have more depending on how we've designed our machine. So our light's going to come out. It's going to go through. Let's put it through an aperture to form the shape of the beam that we want, and to get rid of any light that's not going in the right direction. And we're then going to put it into an interferometer, because the most common type of infrared these days is Fourier transform infrared, and it does not use diffraction gratings to split up the colors of the light. It puts it all through the sample. So to get into this subject, we will imagine this little square of light. So we've got our infrared coming along. It bounces off a half mirror, which bounces off a normal mirror, and then it bounces off another half mirror, which I've put the wrong way around, I see. It has to go that way. So if this is a half mirror, half of the light will continue along here, and half of it will go over here. This beam that goes through here goes straight through, and half of it goes over here and half of it goes over here. So we end up with two beams. Unfortunately, we lose half of our light. We're going to consider this one. This one is made up of two components. The component that went straight through, exactly a quarter of the light, and the component that went round this way, another quarter of the light. And then we get this beam. Because the path length isn't the same, this one is longer, we have a problem. The problem is the two beams are going to interfere, and because it is white light equivalent infrared, it's a lot of wavelengths of infrared at the same time, we're going to have interference of some colors and no interference of others. We'll have constructive interference of some colors, destructive interference of others. Okay, so I had to have a break in between, so I am not entirely sure what I just said. However, for me I'm sure what I just said, obviously, but it was something different to this. So I'm going to go back over to this and we will look at it again. Can't get over there. There we go. So to recap, we've got two different path lengths, this one around here and this one across here. We're generating two beams, which we could put back together if we had a mirror here, but maybe it's not worth it. And we can imagine a new thing happening now. If we take these two mirrors here, let's change colour to green. If we take these two mirrors here and we put them on a carriage that gets longer, we could move them together further away, which means that the beam length is longer again. Bearing in mind that this is infrared light, so the length of a wavelength of infrared light is comparatively long. That makes it a lot easier to do exactly this thing with infrared than it is compared to ultraviolet, obviously, where it's hundreds of nanometers. So we would have to move in a few hundred nanometers, maybe less, 50 nanometer steps, to be able to see interference patterns with ultraviolet light and visible light. But here, because we're a long way away, the infrared region is very big and we're at the long wave end of it, we're in a lot longer wavelengths. So we can go along here and we will see a longer wavelength and we will get a different package of wavelengths that go through effectively. So we have at any length, because it is still long compared to the wavelength of infrared, at any length we will get pretty much every colour getting through, but if we step it a little bit we will change the composition of colours that we have, and we would expect to see at 0, where they're the same length, we would expect to see all of the light come through, and then if we make it longer we would expect to see less light coming through, and then we would get waves in it of different colours. So if we then put that into a Fourier transform, we are converting effectively from time into spectrum, into colour. The time is effectively related to where the position is, so we can, if we move our carriage with these two mirrors on at a constant velocity, time is directly related to position, and then we can convert our spectrum into the full colour spectrum, even though we're always measuring at least, well, we're always measuring several colours at once, usually nearly all of them, but because we are at certain times measuring mostly one colour and at other times measuring mostly another colour, then we can extract the information from it. The good thing about this is called the Multiplex Advantage. Because we're looking at multiple colours at the same time, we get a spectrum quicker. And because we're measuring all colours at the same time, we also use more of our light. We're not wasting most of it because we're not detecting it. So that is our Fourier transform infrared, and the Fourier transform requires us to have an interferometer. If we want to have a 0 offset, which they often do, then we will obviously need to send this second beam, which I've sent straight. That also needs to go on a longer path to make it the same length as the middle of our other pathway. If we look into a spectrometer we can see that, but we can't do that this year. I will maybe try to get a bit of film of one and put it in here.
So this is the interferometer, which is the main part of the IR spectrometer, and it has this hole or area is where the infrared light comes into the interferometer this way, and then there's a stationary mirror right here, and then there's also a mirror that moves over here. Okay, so what we need to have this work is something called a beam splitter. This is going to split the light beam in half, literally. So if I put it in here like this, when the infrared light comes in here, half of it will go through the beam splitter and hit the stationary mirror, and half of it will get reflected and hit the moving mirror. And then those will bounce back and recombine, and we'll use that to make our measurements. Okay, so that's the light source, and it's insulated, so if you look into that little hole, that metal thing is the silicon carbide. That's the actual light source. That's what glows. It heats up and glows, and that's the infrared light source. This is a detector. So the detector sits in the instrument like this, and the infrared light would go into this hole and then get detected in the detector, so we can see how much has been absorbed.
So that was the interferometer, the infrared source, and the detector from a website or a YouTube site called AmiGeo. You can have a look at that if you want to. They're allowing us to use that. This is going to work in very much the same way as the charge coupled device, and very much the same way as other detectors that you will have seen in this course. But I will explain it again in a slightly different way to see if that helps. So if we imagine a normal semiconductor, this would be our filled band at the bottom, which is the same as we would have in organic chemistry as the highest occupied molecular orbital. Then we've got our maybe doping band in the middle, which we'll say is it's an N-type semiconductor, so it's got electrons in, and we've got the conduction band at the top. So to get these electrons to conduct, we have to excite an electron from our doping into the conduction band. That's what we would have to do to get it to conduct, and what would normally happen is it would fall back in, so we have to do something to stop that. And on this diagram, which is similar to the other diagram but it's in a different dimension, this direction is energy, we're going to apply an electrical field to it. If I apply a positive potential to this end, I'm effectively going to bend this end down, and it bends all of them. I'm going to draw it all. So if I pull one end down and one end up, I'm going to do this to it, and this too. Let's not have any states there, and this one. Now the less of it that is straight in the middle, the better. Ideally we wouldn't have any straight in the middle. I've just drawn it straight because if we make it bigger and bigger and bigger, we will end up with a flat piece in the middle. The flat piece in the middle won't do very much. What we're interested in is the bit that is at an angle, so I'm now going to draw it all at an angle. It's also a lot easier to draw. So bear in mind that typically they will be very thin, so that we get a field across our whole semiconductor, and we can bias the whole of the semiconductor. We can bend the bands. This is the conducting band up here, which is where we want the electrons to be. This is the doping band, where there are some electrons, and this down here is full of electrons. So we're going to target this electron here with a photon and pop it up to this energy state, and we can bear in mind that we've got an electrode on here which is at a positive potential, which is pulling that band down, and an electrode here which is at a negative potential, which is pushing that band up, because we're thinking about the energy of the electrons here. If we have an electron here, it will do what things normally do, and it will fall in energy and drop out this end to the positive electrode. If we have a positive hole, so let's let the positive hole appear down here. If we have a positive hole down here, it floats up because it's positively charged. It floats up and goes to the negative electrode. So we can separate our electron and hole pair, which is exactly the problem that we would have if we want to count photons, we need to stop these recombining as much as possible. The way to stop them recombining is to generate a field and to pull them apart to separate them in space. This is not space, this is energy. So if they're above each other, they're actually next to each other and it can just drop straight back in. If we can get it to move, then we've actually achieved something, because it's harder for it to get back and jump back in the hole. Then we can measure the current. We obviously have to apply energy to do that, because to shift this one down and this one up, we are costing energy, but it's a detector. We can afford a bit of energy to power our detector. What we're interested in is counting the number of photons, which we can do by counting the number of electrons that come out the end. If our photon excites more than one electron, then we will measure more than one electron here. This is dependent on how strong our photon is. Obviously, we are now set up with a problem. Let me explain what the problem is. The problem is we can choose this band gap. The bigger the band gap, the less sensitive our detector. So the more blue the photon has to be to excite an electron-hole pair. And if we're going to excite more than one electron-hole pair, such as in the XPS, where it's a photon comes in, it's an X-ray photon, and it excites a number of electron-hole pairs, and we count the electrons to work out what the energy of the photon was. So there we're counting individual photons, and we're using the number of electrons as a measure of how much energy. Then the accuracy of our measure will depend on how narrow we can make the band gap between these two. If we don't have donors in there, then we've obviously got to excite from the bottom right up, but we can measure both the hole and the electron. If we excite from doping atoms in the middle, then the positrons, the holes, might be slower than the electrons, because first of all they've got to form. First of all, this has got to grab an electron from down at the bottom somehow, and then we can let it proceed to the outside. The holes move slightly slower anyway, but our process, or the problem that we're faced with, is the two things. One is, if we excite more than one electron, then we have to restrict the light coming into one photon at a time, otherwise we will not be able to tell whether it was two photons or one that set off all those electrons. So that's a problem. We need to restrict the brightness somehow. And if we have, well, whatever we do, either method, the smaller the band gap, the more good our detector is, either the more accurate or the more sensitive, or the quicker it is. So ideally we would have a very small band gap, the problem then being that thermally, because of heat, we can excite our electron up. And the probability of that happening by chance increases depending on the temperature compared to the band gap. And obviously we're heating it with our light source and with these power sources, so we would need to do something about that, which is why many of these sources are actively cooled. They have a Peltier device and a thermal cooling element on them to keep them cold. Historically, not very long ago, so a decade or two ago, they were all cooled by liquid nitrogen, and now they are mostly cooled by Peltier devices, and that enables them to be able to sort of divide, to be able to calculate out the error from it thermally jumping up and just measuring the electron just from the heat of the material and nothing coming from the outside. Okay, I think that's enough for one time. I will leave you there. See you some other time. I can't be bothered to move the camera back over.